Hi and welcome to the lesson which is on the binomial distribution. So moving on to the warm-up. So let's warm up. Remember, for this topic you'll need to have your calculators. So make sure you've got your graphing calculator handy. If you don't or have your graphing calculator handy, please pause the video and go grab it now because you'll be using it a lot, like heaps and heaps. Right, so let's check it out. So Carl is not having much luck lately. His car will only start 80% of the time, and his motorbike will only start 60% of the time. So draw a tree diagram to illustrate this situation. So we could say on the tree diagram, C for car starts, for example, or M for motorbike starts. So C, you could have C, car starts, C dash could be car doesn't start. So it's 80% chance it starts, 20% chance it doesn't start, therefore. And then for motorbike, you can have motorbike starts, motorbike does not start. Motorbike starts, the complement is motorbike does not start. And it's 60% it starts, so 0.6, 0.4, 0.6, 0.4. So we've made a tree diagram to illustrate the situation. You also have your outcomes. So C and M, C and M dash, C dash M, C dash M dash. On top of that, so you have your probabilities that you can use to answer B. So I've got a tree diagram. Use a tree diagram to determine the chance that both will start. So both will start would be CM. So we're going to work out this probability. In order to do that, you need to work out the probabilities. So remember, with these tree diagrams, you multiply going across and you add if you need to collect any of these together. So that both will start will be CM. So C and M, it means 0.8 times 0.6. So 0.48 is the answer for that one. So probability both start is probability of C and M. And remember, and means multiply. So 0.8 times 0.6, 8 times 6 is 48, so 0.8 times 0.6 is 0.48. And then II, Carl has no choice but to use his car. So what does that mean? So if there's no choice but to use his car, means his car starts, but the motorbike does not. So motorbike does not start, but car starts. So that would be the probability that the car starts, but the motorbike does not start. So no choice but to use your car is only this outcome here. Okay, so probability car starts and motorbike does not start. So that would be probably, so 0.8 times M dash. 0.8 times M dash is 0.8 times 0.4, and 8 times 4 is 32. So 0.8 times 0.4 is 0.32. So moving on, let's warm up. So in a class of 40, 34 like bananas, 22 like pineapples, and 2 dislike both fruits. If a student is randomly selected, find the probability that the student likes both fruits. So it could be a good idea to do a Venn diagram. Venn diagram can help because there might be some overlap between the two. So when you think of it, why is it set up like this? Well, we know we've got bananas and pineapples. We know that 2 dislike both fruits. So 2 is on the outside. And how did we work the rest out? Let's see. So bananas, we know that 22 in total like pineapples, and we know 34 like bananas. So we know that the whole union must, if there's a class of 40, then the whole union must add up to 38, because 38 plus 42 is 40. So if the whole union is 38, then you're able to work out kind of what the intersection of them must be. So the whole union is 38. So 34 plus 22 does not equal 38. 34 bananas and 22 pineapples. Let's see what the overlap is. So 34 plus 22, if you're not sure, try to work it out on the calculator. 30 plus 20 is 50, 4 plus 2 is, makes it 56. So we've got 56 in the middle. So yeah, so 56 is what the overlap is. So what's 56? Take away 38. That will give you what the intersection should be. So these two add to 56. In total, the union should only be 38. So it's 56 minus 38. If you're not sure, use your calculator. Just to prove it, 56 minus 38 gives you 18. So that tells you that there's an overlap of 18. So if there's 22 in total that like pineapples, then must be 4 here, because these two add up to 22. If there's 34 in total that like bananas, this must be 16, because 16 plus 18 is 34. Then check that, does it make sense? Does that plus that plus that plus that equal 40? And yes, it does. And then, so that helps us to work out the probabilities. So B represents pineapples, B represents bananas, P represents pineapples. So probability that they like both, we needed to do the Venn diagram first. So both means the intersection. So it will be 18 over 40. And what does that simplify to? You can divide the top and bottom by 2. You'll get 9 over 20. Next one, likes at least one fruit. At least one fruit means it could like one fruit, like these two, or both fruit. So it's anything inside the union. So it's basically asking, what's the probability of B union P? So in total there's 38, so that these three add up to 38. So there's 38 in here out of 40, which simplifies to divide the top and bottom by 2, 19 out of 20. Now this is getting into the conditional probability because of the word given that. So you need to use the conditional probability formula for the given that questions. So likes bananas, given that he or she likes pineapples. So remember the formula for conditional probability. If you forget it, it's in your formula booklet. Probability of A intersection B, that's meant to be a straight line, intersect B. So no, not intersect. Probability of A, given that B occurs, it should be a straight line, equals the probability of A intersect B over the probability of B. So notice that the thing that is given that has to be the B. So what's given that? Given that they like pineapples. So B is pineapples in this case. So probability that they like bananas, given that they like pineapples. So it's not P given that B, it's B given that P, according to the grammar. So you need to work out the intersect, and you need to divide it by the probability of pineapples. So the probability of the intersect will be 18 over 40, and the probability of the pineapples would be 22 over 40. So you've got to do 18 over 40, so the intersect, 18 over 40, divided by the probability of the second thing, probability of 22 over 40. So what's 18 over 40 divided by 22 over 40? 18 over 40 divided by 22 over 40 is the same thing as 18 over 40 times 40 over 22. And 18 over 40 times 40 over 22, you can cancel down the 40s and you get 18 over 22. And they divide the top and bottom by 2 and you get 9 over 11. So make sure you show the step, 18 over 40 divided by 22 over 40 equals 18 over 40 multiplied by the reciprocal. Because dividing by a fraction is the same as multiplying by its reciprocal. So dislikes pineapples, so P dash, given that he or she likes bananas. So be careful of words like dislike. Probability, dislikes pineapples means P dash, given that should be a vertical line, that they like bananas. So probability that they dislike pineapples is 2 and 16. So the 2 and the 16 comes together to give you 18, it gives you 18 over 40 for dislikes pineapples, 18 over 40 for dislikes pineapples, given that they like bananas, intersection with bananas. So the probability that they dislike pineapples is 18 over 40, but the intersection of dislikes pineapples and likes bananas is 16 over 40. So it's this little crescent here, because it's the intersection of dislikes pineapples and likes bananas. So 16 over 40 is the numerator. The denominator must be likes bananas. So likes bananas is 34 over 40. So you would want to write 16 over 40 divide by 34 over 40. And remember, dividing fractions is like multiplying, keep, change, flip. So it'll be 16 over 40 times 40 over 34. Cancel down the 40s, you would get 16 over 34. and then divide the top and bottom by 2, you get 8/17. So make sure you show kind of like a little bit of working out in between here, like the kind of stuff that I said to write down, rather than what I didn't write down. So out of the warm-up now into the lesson. So in the previous section, we considered the properties of discrete random variables. So discrete ones that only take on fixed values, like 1, 2, 3, 4, for example. We now examine a special discrete random variable, which is applied to sampling with replacement. So like say when you draw a marble out of a bag and you replace it before you pick the second marble. Or you pick a card out of a deck of cards and you replace it before you pick out the next card. So the probability distribution associated with this type of variable is known as the binomial probability distribution, which is what this topic is. So binomial experiments, what are they? When we have a repetition of a number of independent trials, so by meaning like with replacement, in which there are two possible results, success is one result, which is that the event occurs, or failure. Because binomial, like normal, when you think of binary and things like that, you think of 0, 1, like opposites, yes, no. So there's two possible outcomes, there's success or failure. So success is when the event occurs, failure is when the event does not occur. In that case, we have a binomial experiment because there's only two outcomes, hence the bi. The probability of a success, P, must be constant for all trials. So like, in other words, if you draw like you've thought, the probability of draw two cards, probability of the first card being spade is 1 out of 4. But so you have to replace that card so that the probability for a spade for the second one doesn't change. That's why it's with replacement. Probability of a success must be constant for all trials in a binomial experiment. Let Q be the probability of failure. So therefore, because there's all probabilities add up to 1, the probability of Q, of a failure, must be 1 minus the probability of a success. So because all probability, Q plus P must equal 1, because all probabilities have either got success or failure. So hence they have to add up to 1, because probabilities add up to 1. The random variable X is the total number of successes in n trials. So n is how many times you repeated the experiment. So the random variable X is the total number of successes in n trials. So the binomial distribution, what's it all about? So here we have an example of a spinner. So suppose a spinner has 3 blue edges, so 3 blue edges and 1 white edge, and they're of equal size. So then on each occasion it is spun, we will get a blue or a white. The chance of it finishing on blue is obviously 3/4, because 3/4 of the spinner, 3 of the 4 sides is blue, and one of the 4 sides is white. So the probability of a white is 1/4. If P is the probability of getting a blue, then P equals obviously 3/4, and Q must be failure to get blue, which would be 1/4, the chance of failing to get a blue. And it makes sense because P plus Q equals 1. Considering twirling the spinner 3 times, so n equals 3, let the random variable X be the number of blue results in this case, which would occur. Then X could be possibly 0 times, 1 time, 2 or 3 times, because there's 3 spins, so you can get no blues, you can get 1 blue only, you can get 2 blues, or you can get 3 blues. So let's continue this over the page. So from the previous page, so we can represent this on a tree diagram. So we've got the outcome of the first spin, we've got blue or white, or success and failure, 3/4, 1/4. Notice that the probabilities don't change as you go across. So that's required for a binomial distribution. Because on the second spin, it doesn't matter what you got on the first spin. It's still the same probabilities for the second spin. So you got black, white, and so third spin. So first spin, second spin, third spin. Now, the probability of 0 successes, because in this case, a success is defined as being a blue, according to the previous slide. So probability of 0 blues, meaning that it's a probability that all are white. So probability of all being white, remember you multiply going across a tree diagram. So 1/4 times 1/4 times 1/4. so multiply the numerators, multiply the denominators, you get 1/4 cubed, or you can think of it as being like 1/64, same thing. Probability of 1 blue. So 1 blue and 2 whites. There's a number of different outcomes. You can get 1 blue and 2 whites. You can get blue, white, white. Or you could also get white, blue, white. Or you can also get white, white, blue. So there's 3 different ones. And so you've got to individually work out their probabilities. So the blue, white, blue, 3/4 times 1/4 times 3/4. That's this one. And then the white, blue, white, 1/4 times 3/4 times 1/4. And so on. And then you can do one for the white, white, blue, 1/4 times 1/4 times 3/4. So overall, like a simpler way of doing that is you can think of that as being 3/4 times 1/4 squared times 3. Because in this case, see, it's all 3 cases were 1/4 times 1/4 times 3/4. See, 1/4 times 1/4 times 3/4. 1/4 times 1/4 times 3/4. So it was always the same. So probability of 2 blues, 2 blue and 1 white. So you can have blue, blue, white. You can have blue, white, blue. You could have white, blue, blue, and that's all. So work out those probabilities. You might see a pattern: 1/4 cubed, 3/4, 1/4 squared times 3, 3/4 squared, 1/4. So a simpler way of working it out. They're basically all black, black, because black is always 3/4. So 3/4 times 3/4 times 1/4. 3/4 times 3/4 times 1/4. 3/4 times 3/4 times 1/4. So that's why it's been summarized here. And then the last outcome, 3 blue discs, blue, 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 that's 3/4 cubed. So you've got so you might notice some pattern in 1, 3, 3, 1. Might seem like a familiar kind of pattern to you. So the coloured factor 3 in this first one is the number of ways of getting 1 success in 3 trials. So meaning it was 3 times that. Because these 3 things had the same probability, so that's why we just took 1 probability and times it by 3. Same with this one. So do you remember from binomial theorem that you could use something like NCR, or you can write it as C31. So C31 meaning that 3 spins and chance of 1 success. 3 spins, 3 trials, 1 success is what that means. Another way we've kind of might have written it in the past as 3C1, like that in binomial theorem. So it's the same thing. You can change it to that if you want. So do you remember you learnt how to do this to work out 3C1? 3C1, you learnt how to do it on the graphing calculator last year. If you've forgotten, I'll show you. So if you wanted to work out 3C1, remember you go math, probability. Go across to probability. There might be another way to do it, I forget. CNCR is the third one. And you can put in 3, 1. And you get 3. So that's where the number 3 comes from. It's like from Pascal's triangle, 1, 3, 3, 1. But remember, you can also work it out by hand this way. If it's with calculator, it's easy. Just use the NCR button. If it's not, you have to do it by hand. So 3, 1, you would have to put in 3 factorial, so 3 times 2 times 1, 1 factorial, which is 1, n minus r factorial, which is 3 minus 1 factorial, so 2 factorial, 2 times 1. So you'd have to work out 3 times 2 times 1 over 1 times 2 times 1, and then you get the same answer, 3. Okay, so we have noted that from the previous one, we've kind of got this 1, 3, 3, 1 thing going on here. And then similar to binomial theorem, the first probability of a failure cubed, probability of a failure squared, probability of failure 1, and then no probability of a failure, or probability of a failure to the power of 0. Same thing, the probability of a success increases by 1 with the exponents. Very similar to binomial theorem, hence why it's called a binomial distribution. So if you work those out with a calculator, you would kind of get these approximate values. What do you think they all add up to? They all add up to 1. And if you graph them, if you graph the heights, so 0.156, 0.0156 is this little one, 0.1406, 0.412, 0.4219, you kind of get this binomial distribution as well. This suggests that probability of x, C3x, is 3/4 x, 1/4 3 minus x, similar to binomial theorem and so on. Or in that case, it's that. And this thing, remember, this thing here comes from, just pointing out where it came from there. Like NCR, you can write it as NR in the bracket like that. In general, in the case of n trials where there are R successes and n minus R failures, probability that x equals R is NCR, the binomial coefficient, p to the power of r, q to the power of n minus r, similar to binomial theorem, where q equals 1 minus p, so that might be something you might need to sub in at some point. And r is 0, 1, 2, 3, 4, all the way up to n experiments. So n is how many times did you repeat the experiment? P is so hence in this case n was 3, because we did 3 spins. X equals r is a binomial probability distribution function. So binomial NP is useful notation. It indicates that the distribution is binomial and gives the values of n and p. So that might be a notation you might see coming up. Okay, so fair enough if that seems confusing, so we just need to do it through examples. A binomial variable is often specified in the form binomial bracket n, comma p. N stands for the number of trials, p stands for the probability of a success. They don't bother to put in q because q is just 1 minus p. The binomial coefficient could be written like this, or in our case it could be NCR in our textbook sometimes. So for binomial distributions, the probability, so just a reminder, the probability distribution must be discrete and not continuous. There are 2 outcomes, which we usually call success and failure. The trials are independent, so the probability of success for a particular trial is not affected by the success or failure of previous trials. So anything is done with replacement. In other words, the probability of success is constant for the experiment being considered. A binomial distribution is a discrete distribution defined by 2 parameters, the number of trials n and the probability of a success p. So you write, a notation you might start to see is x, and a little wavery thing, b for binomial, n stands for the number of trials, p stands for the probability of success, to indicate that the discrete random variable x is binomially distributed. So you need to be able to understand that this notation is trying to tell you that there's a binomial distribution. Rather than write it as a sentence, they can use that notation. Let's apply it so you can see how to use it. Shooting Annie. Annie is trying her skills at a shooting range. In a round, she has 3 shots, and the probability of a success on any shot is 1/4. So P is defined as being 1/4. Annie is interested in the number of hits or successes in any round and lists the possibilities in a table. So possibilities in a table. And note, because notice there's 3 shots. So 3 shots was important, like n equals 3, P equals 1/4. So therefore Q equals 1 minus 1/4, which is 3/4. So the possibilities in all of them is you can get a hit, 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 miss, hit, miss, hit, miss, hit, 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 and so on. Basically, if you did a tree diagram, you'd get all these kind of outcomes. Number of successes, so 3 hits, so that's 3. Here there's 2 hits, 2 hits, 2 hits, 1 hit, 1 hit, 1 hit, no hits. So hence why there's 3, 2, 1, 0. Probabilities, like hit, 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 is that. So hit, hit, miss, 1/4 times 1/4 times 3/4, because a fail, a miss is like a fail, which is 1 minus 1/4, or 3/4, and so on. And then let x be the number of hits, i.e. the number of successes. X has a distribution shown. So you could summarize it in a table, so the outcomes are either 0, 1, 2, or 3. 0, 1, 2, or 3. So the probabilities here, where on earth did these come from? There being a 0, there was only 1 0. So you just have that one there, 27/64. But there were 3 different versions of one success, and they all had the same probability. So it's 3 times 9 over 64. There were 3 different versions of 2 successes, and they all had the same probability. So 3 times 3 over 64, and only 1 version of 3 successes, and so on. It's kind of how you could work it out. In this example, note that the outcome of the experiment only comprises success, which is a hit, and failure, so hit or miss. We also notice that we have assumed that the probability of success was the same for each trial, and that each trial was independent of the others. Whereas in reality, maybe like she might get more tired the more sort of hits she's had, so she might have the chance of a success might become lower with more hits. But in this one, we've made the assumption that it's always a quarter. So here's the only example continued. In the example, note that the outcomes of the experiment only comprise success, hit, and failure, miss. So this is basically just copied from the previous slide, just reminding us of that. So the distribution of x is a binomial distribution. The binomial distribution function is given by, as we said, it's like the binomial theorem. Probability x equals r is the binomial coefficient, like 1, 3, 3, 1, or each one. Probability of success raised to the number of successes. 1, and the probability of failure, q, which is 1 minus p, raised to the power of the total number of experiments, minus the number of successes. Where p is the probability of success and NCR is a binomial coefficient, which if you were to work out by hand is n factorial over r factorial brackets n minus r close brackets factorial. That's how you work it out by hand. It's common to write q equals 1 minus p, like here. Rather than write p and q, you can just sub in 1 minus p in this case. So it's the more simple ways of putting q. Notice that NCR is the binomial coefficient of PR and so on in the expansion, in the binomial expansion of that. Back to trying to relate it to binomial theorem. And so on. So I might just stop this here because I have to rush off for an appointment, and then I'll continue this in part 2 soon, and I'll upload it as well.